This is a video lesson on the 3D theorems used to optimize volume and surface area. So for 3D solids. Theorem number 1 says that of all solids with the same total surface area, the solid with the most faces will have the greatest volume. And this is very much like the 2D theorem that said that for all shapes with the same perimeter, the shape with the most sides will have the greatest area. So instead of sides, we're talking about faces, and instead of greatest area, we're talking about volume. But the conclusion is similar to what it was in 2D. In 2D, remember, that meant that the ideal shape, the ideal 2D shape was a circle. For 3D, the ideal 3D solid is a sphere. It's effectively the solid with infinitely many very tiny faces. So for 3 solids that all have the same total surface area, if you worked out the volume of this, and so I would have to work backwards and say, okay, there are 4 equal faces, then break up those faces to figure out the side lengths and the slant height and the height and do some Pythag calculations. It turns out that the volume of this solid is 300 and change meters cubed. And same thing here. If I knew that the total surface area was 300, there are 6 equal faces. I would divide this by 6. That would tell me the area of each square. I would take the square root. Then I would know the side length, and then I can find the volume. And the volume here is about 353.55 meters cubed. So this one is significantly greater in volume, even though they have the same area. And this shape, a sphere, if I knew the total surface area, I could solve for the radius, and then using that could solve for the volume. And the volume here works out to be a lot larger than either one of these two, all with the same area. So in conclusion, if you have a choice of the solid, sphere is the best one. Theorem number 2, of all solids with the same total surface area and the same number of faces, the solid which is the most regular will have the greatest volume. So that means that the dimensions are closest to equal. And what that means is that if you don't have a choice of the number of faces, then you want the shape to be the most equal possible. And the most common type of question that will come up is with a prism. So a prism will have to have, supposing it's a rectangular prism, will have to have 6 faces. And for that to be the most regular will mean that all the sides are equal or as close as possible. And if you can choose all the dimensions, you'd want it to be a cube. That would be the best one. So of all rectangular prisms, cube, or the closest possible to a cube, will have the best ratio of volume to surface area. And the last two are very much like they were for 2D. They're sort of the same ideas, but working backwards. Of all solids with the same volume, the solid with the most faces will have the least surface area. So this is just the reverse of what we had said in theorem number 1. But again, it means that if you can choose, a sphere will be the best shape. And the fourth one is the same as the second, but backwards for all solids with the same volume. The one that is the most regular, if the number of faces remains constant, will be the one with the least surface area. So again, the idea here is that if you can, let's say in a rectangular prism, not change the number of faces, you can at least choose the dimensions, and you'd want it to be as cube-like as possible. An application in 3D that we don't really see in 2D is how to package a certain number of items together. And when you do that, you want to do it in a way that minimizes the surface area of the packaging. And that means that you have to follow those rules. So you can choose a sphere if the constraints of the thing you're packaging allow for that, but sometimes they don't. So often you will have to package things together in a way that they can be packed in a box, which would be a rectangular prism. So questions like that will be covered in a separate video lesson.